So we have a 1,000 kilogram car, and there's a high wave curved, and a radius of curvature of 100 meters. Okay, it's banked at an angle 15 degrees. So the radius here is going to be 100 meters of this turn that it's making here. Suppose the pavement is dry and the coefficient of static friction is 0.2. In this problem, we will determine the range of speed which the driver can safely around the turn without skidding. Let's assume the car is going at minimum speed, so it can make the turn but does not slide down the incline. So why like, and we're assuming that like it's going really slow. Like, just pretend it's barely going slow there. So let's draw the free body diagram here, okay? And they give you some hints here. So first we're going to do gravity, just like we did in the first practice problem. We got mg. We have a surface here. It's going to be perpendicular to that surface. So this looks like just like the other practice problems when we had no friction. But now we have friction. We have to think about it. The rule for friction on the surface is it's parallel to the surface. Now, is it up the ramp or is it down the ramp? That's what we have to decide. We don't know if it's up or down the ramp, okay? Now, they give you some hints here. There's a couple ways to think about it, and I'll help you understand this. So they're telling you that when it's going too slow, there's not enough centripetal. The normal force is not enough to provide the centripetal force, centripetal acceleration. So that means the friction has to aid it by let's see, by going the normal force is not enough. I don't think that's right. I don't think that was phrased correctly. Let me fix. I'll have to fix that. But basically, the normal force is too large. Actually, the normal force is too great of a force. It's going to be more because the centripetal acceleration is really low. Gotta imagine the v is close to 0. There's almost no centripetal acceleration. So that means one way to think of it is the frictional force has to be up the ramp opposing that. The other way to think about it. Okay, the other way to think about this is that the frictional force, like remember what I said with static friction. Static friction is always difficult to determine. Imagine there were no friction and this guy were just sitting there, low speed, velocity is 0. There's no friction happening, and if there's there's no friction. So what would happen is that it would just be like an inclined plane block. It's just going to slide down the ramp. Okay? So the frictional force is going to oppose that. It's going to prevent it from sliding down the ramp, going up the ramp there. So that's how we know for the minimum speed, the frictional force is going to be up the ramp. It's going to be opposing that. Now, okay, so that is the free body diagram. Now we got to do the Newton's second law. So what's the next step? We got to identify the acceleration. Acceleration is centripetal. It's directed towards the center of the circle. Okay. Cool. That means we are not going to decompose them like an inclined plane. We're going to decompose the forces as this is x and y because we always want our acceleration to be parallel to the x-axis. It just makes the math easier. The math is just simpler if we do that. Now, all of these angles here are 15 degrees because that's how it's tilted, or this thing. So then we're going to decompose the normal force into Fn sine 15 degrees and Fn cosine 15 degrees. And remember, careful with the arrows. It goes up and left, just like it has to follow this path here. How about the frictional force? It's got to go right and then up to make that right triangle. And this is the frictional force cosine 15 degrees. This is the frictional force times sine of 15 degrees. Okay? Now we've decomposed all the forces. We need to decide which way is the positive directions. The left is positive and up is positive. In the x direction, we'll do F net equals ma. What are all the forces in the x direction? Well, the Fn sine 15 degrees is to the left, so it is positive. The FF cosine 15 degrees is to the right, so that's negative. And those are the only horizontal forces. There are no other forces in the x direction. And that equals mv squared over r, because the acceleration is in the x direction. All right, that's what the A is, centripetal acceleration. How about the y forces? Okay, any upward forces are positive. Fn cosine 15 degrees is up. The frictional force is also up, so that's positive. Or the sine 15 degree component is, and then mg is down, so that's negative. And this has an acceleration of 0 because there is no vertical acceleration, just like the previous ones. It's just moving in a circle like this. It is not going up or down or accelerating up or down in any way. Okay, We know M. We're trying to figure out V. Okay, all right, so determine the normal force acting on the car. What key assumption do you have to make to find the normal force? Okay, so right now we just found the equations here. Okay, like this. Okay, now we want to solve for the normal force, and we're going to assume something here about like, if you look at this, there's three unknowns. Fn is unknown, the frictional force is unknown, and the V is unknown. So three unknowns, only two equations. This is not solvable yet at this point. Okay, but we can think, because we know mass, we know R, right? We know G. We can think about, like, what is going to happen at this point is if I want the minimum speed, I want the frictional force to be maximum, because any slower than, because the frictional force is helping prevent it from slide down the ramp. So if we go any slower, we're going to need more friction to keep it up the ramp, and we're going to exceed the maximum static friction. So this is the key assumption, at minimum velocity, the force of friction has to equal the maximum frictional force, static frictional force, which is mu Fn. This is our key assumption that we have to use. Now, I don't want to use this equation because I don't know V, but I can use this equation because I can then plug in this into the frictional force. So I get Fn cosine 15 degrees, plus mu Fn sine of 15 degrees, and then just move the mg to the other side. And look at this, I can factor out an Fn. To get mg, and I can solve now for the normal force. Okay, so let's do that. So that's going to be, the m was 1,000. And we use cosine 15 degrees. What was the mu? The coefficient of static friction was 0.2 sine 15 degrees. And it's coefficient of static friction because that's the kind of friction that's happening here right now, right? And that equals 9,630 newtons. So that's the normal force. Now that we know the normal force, we can find the frictional force, and then we can solve for V over here. Okay, so the frictional force is, again, 0.2, because it's the maximum frictional force. It's 0.2 Fn, which is 0.2 times 9630. And that's equal to 1926 newtons. And then we can use this equation over here to find the V there. So this is going to be 9630 sine 15 degrees minus 1926 cosine 15 degrees is going to equal m, which is 1,000, times v squared divided by 100. Okay, so then we're just going to solve for v there. That sine 15 minus this number cosine 15, 10, and then square root of that. I get v is 7.95 meters per second. Okay? Now let's do the maximum speed. Now we're going to go super fast, faster and faster and faster and faster. What's going to change in this scenario? Well, the gravity and the normal force don't change because ultimately those surfaces haven't changed, right? If we look at the picture, just because we're going faster isn't going to change this. However, the frictional forces, here the centripetal acceleration is what the normal force can provide. In that case, what should the direction of the static force be? This is going to be down the ramp, okay? So we're just literally just going to make it go down the ramp instead of up the ramp. And now why is that going to change? Why should it go down the ramp? Because what would happen is if you go too fast and there were no friction, right? That's the trick with static friction. Pretend there were no friction, okay? And you were going too fast, then you would slowly slide up the ramp. Imagine trying to take a turn really fast. What happens is you slide off that path because you do not have enough force to do that centripetal acceleration. So instead what happens is friction has to assist you, prevent you from sliding up the ramp when you're going too fast. That's why it's down the ramp. Now, if you actually think about it from a shortcut on this, so what's the normal force on the car? Now, think about if the centripetal acceleration is still to the left. The only thing different in this scenario is the direction of the frictional force. So honestly, it's going to be the same equations, but everywhere the frictional force is, you're going to flip the sign because it's pointing the wrong way. Okay, so this is 15 degrees, this is 15 degrees, and then again, we'll just do the decomposition, right? Fn sine 15 degrees, Fn cosine 15 degrees, and all you will notice about the difference between the two is really just the frictional forces pointing the opposite direction. If you look at a comparison, let me just grab this as a comparison point. Okay, just side by side on them. Notice that the only difference between the two free body diagrams, the normal force is the same, the gravity is the same. It's the friction. Instead of being right, it's left. Instead of being up, it's down. So you can honestly, to shortcut this, you can take your same equations here, and you're just going to flip the signs of the frictional force because they're literally just pointing the opposite direction. So instead of this being minus, you can make that plus, and instead of this being plus, you can make that minus. And again, our frictional force should equal the maximum static frictional force, which is mu Fn. And so you can even, like, see how we solved this thing over here? You can actually just take this equation and put a minus sign here. Because basically, it's just, instead of plus, it's a minus here. So, like, when I plug this in, Fn cosine 15 degrees is going to be minus mu Fn sine 15 degrees equals mg. And so the normal force is going to be, if you factor it out, it's going to be mg over cosine 15 degrees minus mu sine 15 degrees. Almost the exact same, just with a minus sign. So actually, you could save yourself a lot of work if you do this. And I get 10,720 newtons, which means the frictional force, which is mu Fn, because it's the maximum static friction, it's just going to be 0.2 times that number, and that's going to be 2144 newtons. Okay, and then we can use that to solve for V over here. So we're going to get 10,720 sine 15 degrees plus 2144 cosine 15 degrees equals 1,000 is the kilogram, m, v squared over r of 100. And you could solve for v at this point. Okay, so that times sine of 15 plus this number times cosine of 15, 10, and let's take the square root, is 22 meters per second. So this road, the way it's designed, the slowest you can go is 7.95 meters per second. The fastest you can go is 22 meters per second. Anywhere in between, the frictional force will just not be at maximum. We found the maximum in each direction, and that gave us the range of the velocities that it could be at.